started. So the attendance code is German, and so we will be discussing finite as well as infinite horizon value iteration. And then actually for the infinite horizon, there is also a policy iteration that we probably won't come to today. Then in which case we'll talk about next class. And so before, first of all, I'm assuming that all of you have looked at the walkthrough of the finite horizon value computation, because I'm just going to go through it quickly today. But since you already did that, you have a sense of value of a state, and you also have a sense of reward of a state. So my question that I asked you to think about is this statement true or false? The value of a state is proportional to its reward. How many of you think it is true? Raise your hands. So you think that the value of a state is proportional to the reward. That's of the people who raise their hands. Okay, how many think it's false? Why are the rest of the people actually in the class? Right, you should have an opinion. There's no point in showing up if you have no opinion about what's going on here. Let me ask again. Value of a state is proportional to its reward. How many people think it's true? Okay. How many people think it is false? Okay. So, here's the deal. Let's just get this once and for all out of our minds by taking an example. Here are two states. State 1, hang around outside in the good weather. I don't know if you guys noticed, beautiful weather. It's like the first of the beautiful days. State 2, come to Rao's class. Okay? About rewards, you can be honest, right? I mean, even in my wildest dreams, do I believe that people think hanging around outside is less interesting than being in my class, right? So the immediate reward of being in this class is somewhat negative, kind of meh. Especially on this beautiful stuff that's going on outside, okay? I mean, I try to make the class interesting by telling a few jokes, this and that, but honestly, who are we kidding? Okay? Would much rather hang around outside. Okay? So, if you want to make up some numbers, the reward for this seems to be kind of like plus 100. The reward for this is like minus 0.4 or something. Maybe minus 0.7, whatever, who knows? Okay? That's its reward. Now, what's the value of these two states in life? And remember what you're saying. Right? Because you hang around outside enjoying weather, that's about it. Okay, there's not much major things you can do because you enjoyed the weather. You come to this class, lots and lots of opportunities open up. Your grade improves, your mind opens up, your more job opportunities open up. So the long-term reward is like one of these Visa commercials. It's priceless coming to the class. Right? Do you understand what I'm saying? So, is the value of these two states proportional to their rewards? If you ever have a question as to whether or not value is proportional to the reward, think about hanging around outside versus coming to my class. And even after many, many years, the wounds will still be fresh. And you will remember that the immediate reward of being in the class was rather raw. It wasn't very good. And yet, you will be enjoying your Google salaries. Right? You understand what I'm saying? So in fact, this is like the most important thing about Markov decision processes that people have to understand. That the reward is not proportional at all. It's not actually related at all to the final value. would you prefer if I give you two different MDPs, one in which I just somehow make the reward be proportional to the value, the other in which the reward to be it doesn't have to be proportional to the value. Which would you rather prefer as an agent? The first one, right? Because essentially that way you don't have to use your brain. You just say, this thing looks sweet, must be good for me. This is not good, and this is not sweet, so must be bad for me. You see what I'm saying? And the people in our lives who don't have particularly big brains, other than some of us, are little kids. Okay? So you make sure that when you build a home, build a living room, you make sure that you don't make your gun the shiniest object in the home. Right? Because kids think shiny objects, especially if you also put some candy on it, they'll think, wow, that's a nice thing, tick, 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 tick. And then you understand what I'm saying? Okay? So, in general, so this is very deep points. Don't discourage. The very deep points. In general, write this down in your head or somewhere. Reward value is not proportional to reward. In fact, most of the reason people screw up in life is because they go for immediate good reward. Haven't you heard of delayed reward? Delayed reward is all life is all about. Okay? The people who are out there enjoying, some of these people who are not here, who are out there, they didn't get the concept of delayed reward. Also, I would like to believe. Okay? And the point, of course, is that in general, value is not proportional to reward. If you can make reward be proportional to value, the agent's life will be much easier. In particular, the agent can be myopic. This is a word that you should use on your friend, saying, stop being so myopic. Okay? Myopic means looking only in front of you, not looking ahead. Okay? In worlds where rewards are proportional to the final values, local decisions based on what is in front of you also wind up being globally optimal decisions. Normally, that's not true. Okay? So, if in fact, in the kids' case, what we were doing is, you can stabilize the environment by reward shaping. So for example, if I wanted to be nice to you, I realize that I want you to get your Google jobs. I realize that you don't want to come to the class. So I will say, I'll be getting candy every day. Right? I say, oh, there's candy, instead of outside, candy inside, I'll come here. And then we'll close the doors and teach you. Right? Why do I actually do that? If, in fact, I want to make sure that you will do well in your life, then I might do it, even though people might actually put me in jail and stuff. That's basically reward shaping. In fact, there's this funny quote that, Homer Simpson. How many of you know Homer Simpson? How do you make Homer Simpson go to the library? Put donuts all the way to the library. Do you see what I'm saying? That's reward shaping. So, given an MDP, it may or may not be the case that the reward is proportional to the final value. In general, this is not at all true. in good MDPs, like very easy MDPs, where local decisions will wind up being optimal, it turns out that either that it is the case that rewards are actually proportional to the value, or somebody took time to make the rewards be proportional to the value. Okay? Reward is think of reward as local gradient. Value, optimal solution. It's related. Reward is related to the local gradient. Value is related to the finally optimal solution. You see what I'm saying? And so, if you can, in general, the reward is not at all proportional to the value. That is something that you just have to understand. You can have a highly positive reward for a state whose final value is highly negative. That was the case maybe for this. And a highly negative reward for which actually the value is highly positive. So this is, for example, by the way, reward shaping is done all our lives because we just don't live in the world that is given to us. We change the world we live in. Right? Do you really believe that medicines are sweet? All the medicines you ever took are sweet. Right? When you put a tablet, most of at least especially the kids' tablets, it's fun, they're like nice and sweet. They make it sweet, just so that kids will eat it. Your kid is not going to say, yeah, no, I should really be taking this really, bitter medicine now because 15 years later I have to go to AI class and then I should get a Google job. Kids don't think like that. Since parents are into making kids do well, and the society is into making kids do well, they reward shape the heck out of the world. Okay? Understood? Questions? Yes?
So, in the case when you have a finite horizon problem and n values are small, don't the final states, don't they depend on the rewards of the individual state? For example, in the example that video that we saw, the one that said 10, the first state, that ended up having a higher value than the others.
It's not, actually, that was just true of that particular, so immediate reward. So first of all, the final state, whatever you're saying final state is just reward, immediate reward of being in that state. Okay? Immediate reward of being in a state at that particular time, that is when the end of life being in that state, is not at all connected to its reward k steps before. And it is connected to the k steps before only in terms of this expectation maximization. Okay? By the way, if you think in terms of rewards, this looks surprising. If I just ask the following question, if you have evaluation functions in the game tree, and you could have just basically looked at the evaluation function value at the first level itself, or gone deeper, applied the evaluation function and set it up. If the evaluation functions were actually proportional to the final backed up value, did you understand what I just said? Then why should you go deep? There's no reason. It's only because evaluation functions may or may not be at all proportional to the final value. Must you go deep to make sure whether or not actually the backed up value is a true indication of the value. Reward is not at all indication of the value. In the case of game trees, we call rewards evaluation functions. These are things that you want to keep in your mind because otherwise they're just topic 1, topic 2, topic 3. They're all connected. Yes?
In MDP, the look ahead is not a characteristic of the MDP.
It's a characteristic of the agent. Exactly. Yeah. MDP is an environment. So this is the environment we are living in. Some people came into the class, some are still outside. That's not different about the environment. It's their decision.
And we are saying the reward is not proportional to the like the step reward. It's because at the end state we have the exit reward as well.
No. I mean, no. If you should understand this stuff. Immediate reward of a state has nothing to do with the final value that you can achieve if you were to start from that state and live a long enough of time. Remember, the value of a state is really not directly the property of the state. Value of a state is a complex combination of the reward of the state, the actions that you have available, the states those actions will take you to, the actions you have available at those states, and the states that you will go to. That's what was being done in the finite horizon MDP computation. It's not obvious at all what is the true value of the state. That's why you search. If in fact there is any obvious connection between reward and value, we shouldn't be wasting our time talking about MDPs. You just do the obvious, just take the reward and then go to the state that has the highest reward and you're done. And also remember that you hear this reward shaping thing a lot. And I explained to you what reward shaping is. Reward shaping tries to make reward be sort of proportional to the value. Okay? Good. So, let's go forward now. So, we are going to talk about finite horizon MDPs, and I'm just basically going to walk through the slides. So, we are looking at the value of a policy first, and then we look at how to compute the optimal policy. Okay. So now to decide how good a policy is, you have to talk about the accumulated reward of following that policy starting from this state. So if you are in some state, S, then using this policy, you can get one trajectory. You again use the same policy, you might get a different trajectory. Again use the same policy, you might get a different trajectory. Right? The reason you get different trajectories is because if you do the same action, sometimes it goes to state 1, sometimes it goes to state 2. It's probabilistic. And so anytime you have a trajectory, you can compute the cumulative reward. You can add up the immediate rewards of all the states on the trajectory. Now if you're following this policy pi, even though it looks like every time you run the policy pi, you're getting a different trajectory, they all have more similar to each other, than the entire set of all trajectories of the world. Because you're still doing only, let's say, action A1 at state S1. And A1 will, let's say, will with 0.7 probability take to S2 and 0.3 probability take to S3. It won't take you to any other states. Right? Just because there's some randomness doesn't mean it's uniformly random across all trajectories. So when you are in this state, you basically consider a bunch of trajectories, compute the cumulative reward, add up the rewards, you get cumulative reward, take the average of them. That is the expected cumulative reward of starting from S and following this policy regularly. Remember, when I'm talking about finite horizon, the policy is of this type, pi sk to A. The policy pi says if you are in state S and you have k stages to go, then you must do action A. That's what the policy would have told you. Okay? When I'm saying I'm simulating the policy, then I'm here, let's say if this is total k states, then here I'm basically taking pi sk, and then at this level I take whatever the state k minus 1, pi s dash k minus 1, then the next level I take pi s double dash k minus 2, etc. So I'm doing this in the back of my calculations. Okay? If I do this, I will get these trajectories. I add up the cumulative rewards, I take the average, I'll get the expected value. This is the value of the state. So you have a brute force way of doing it. In general, in computer science, it's important to first know whether you can do something in the brute force way. And then be a computer scientist and say, can I do it in a better way. Right? So, in case you forget about this, a brute force way of doing sorting of a sequence is given a set of numbers, you find all its permutations, and check if any of those permutations is sorted. Simple. Just unfactorial permutations, and checking whether something is sorted is much cheaper. Now, if you try to do this, then they'll throw you out of the job. Because it turns out that instead of doing this generate and test, you can actually put the test part of the generate test into the generate part. That's what sorting actually does. In fact, Minsky, I think, has said at some point of time, intelligence is putting the test part of generate, test, debug into generate part. Very deep statement. This is how you actually improve algorithms. You start with a dumb idea and you improve the algorithm by not even generating trajectories not even generating solutions that can't possibly be right. Candidate solutions that can't possibly be right. In the case of sorting, what you do is if you already have a subsequence which is unsorted, then you don't try to consider all its extensions. Because if you're dead in one place, you're dead all over. That's the truth of sortedness. It's not actually true if you're saying, do as much sorting as you can. So if I change the definition of sorting problem to say, what is the optimal amount of order you can put in your room before your mom comes home or your dad comes home and yells at you saying, why is everything everywhere? That's an optimization problem. There it is not clear that a partially unsorted sequence cannot be extended to become a globally optimal one. But normal sorting, a partially unsorted sequence, you can kill it. The reason I'm saying this is this idea that I showed you is the brute force way of computing the value of a policy. If you have nothing else to do, this is what you will do. You basically simulate the policy, get the trajectories, add up the reward numbers, take the averages, put that as the value. But then what you realize is there is actually a structure to the values of the states with respect to the horizon. The first insight you realize is if you have 0 stages to live. If you are in state S, you have 0 stages to live, then you are never going anywhere. Whatever you are is the place you are dying. So if you have 0 stages to live, your reward is your policy, your value. Do people understand this? If you 0 stages to live, your reward is your value. Okay? So then what I will write is essentially V pi 0 of S equal to R of S. That's the base case. So we already know V pi 0 of S. And then I just need to compute V1 of S in terms of V0 of S, V2 of S in terms of V1 of S, and so on. Why? Because it turns out that just like sorting has some structure, you essentially have structure to the values of states given a policy. Okay? So the example here basically is V0 pi of S is R of S. And then Vk pi of S, that is k stages to go value of the same state S, is R of S plus, now since I'm using pi, basically there is something saying pi sk. What is the action? Pi sk is an action. That action will tell me the states I can go to. This transition function here is basically saying if I do the action pi sk in state S, what is the probability that I'm going to S dash? So if, for example, this is an action which winds up taking you to state S2 with probability 0.7, S3 with probability 0.3, and 0 everywhere else, then most of this will be zeros for S dash, except for S dash equal to S2, S dash equal to S3. Right? And so those are the probabilities. And then once you do that, so if you actually were to go to S dash, then from S dash you're going to live with for k minus 1 more steps. Do you see what I'm saying? So you essentially connected the value of the policy pi with respect to k stages to go of state S to the values of its neighbors as defined by the policy. So your neighbor is the one that your policy can take you to. Do you see what I'm saying? And their values with k minus 1 steps to go. And this computation will peter out with k when, k minus 1, k minus 2 up to 0. At the 0th stage, you know what the value is. So you back propagate that. That's what you do. That's what value computation is. Now, if I just tell you this, yeah, what else will you do? But remember, if you were doing this, then you would act as if every state is completely disconnected with every other state. In trying to compute a value of state S1, you will do a huge amount of empirical simulation, take the cumulative reward, take the average. For its neighbor, do the same thing. For its next neighbor, do the same thing. Every state, you do the same thing. You are not realizing that the values, this is real estate all over again. Value of our house depends on the value of your neighbor's house. Which is why in US in particular, people are very mean to their neighbors. If you don't clean your front yard, in fact, I think Dave Barry says that in US, people are generally happy to have rapists, druggists as neighbors, but not people who don't clean their front yard. They don't clean their front yard because their house value is going down, your house value is going up. Right? That's the same thing is happening here, that your values are defined in terms of your neighbor's values. Where the neighborhood is in terms of the policy. And if I don't use that, then I'm trying to compute each value of each state independently. So I waste a lot more time. So you, just as you really appreciate sorting after you think of first the idea of, let's just take a permutation and then test whether it's a sorted sequence or not. And that's n factorial. And then if I give you even an n square sorting algorithm, you say, man, you're smart. Right? So this suddenly is a much smarter idea. And what is it? Why is it able to do this? It is able to do this because the value of a state depends on value of its neighbors. Okay? That's what we did. Okay? So how can we compute Vt1 plus S given Vt with respect to some policy pi? I threw in some numbers here. The base case is V0 of Si with respect to policy pi is R of Si. And then by, the computation goes right to left. The rightmost case would be, S1, S2, etc. at 0th level. So V0 of S1, etc. So you have their values already because that's the reward. And for these guys, S, I'm in state S, and have t plus 1 stages to go. And the policy tells me that if I have t plus 1 stages to go, I'm supposed to do action A1. That's what my policy told me. This is the policy I'm trying to evaluate, how good this policy is. Right? Okay? And then I take A1. It turns out A1 will take me 0.7 probability to S1, 0.3 probability to S4. So then I would basically consider this computation 0.7 times t stages to go value of S1 plus 0.3 times t stages to go value of S4. right? Add that to RS, I get VT1 plus S. Even though there are variables here, when you are computing the value of the policy, you just basically you already have V0S, so you get V1S directly as numbers. V1S, you get V2S as numbers. V2S, you get V3S as numbers, all the way up to VKS. You guys got it? This is the way we compute the policies value. This is the way we compute the value of a policy. Value of a particular way of living. A policy is a particular way of living because it's telling you in this state, if you have so many years to go, do this. So for example, a policy, if you are still young, and you are in this, you have young means you have so many more years to go, then it's basically going to tell you the policy value that you get if you hang around outside versus policy value you get if you come to the class. My assumption is that when you're really, really, really old and your brain isn't working anyway, you might as well hang around outside. Okay? Yes? Yeah.
Is there a relationship between the probability of getting to a state versus the heuristic cost of the strategy?
No, not at all. Again, all of these are independent units, and it's extremely important not to make up relations that don't exist. And the one that I gave you is the relation that everybody hopes exists, which is the reward must be connected to the value. Unless you have some gods or rich uncles reward shaping the heck out of your world, that's not true. Okay? That's one of the good things. If you have rich uncles or gods, you don't need brains, because they'll do the thinking for you. And you can just do local gradient following. The rest of us better have brains, because this computation is needed. This is for value. Okay, so the next question is, now you computed the value of a policy. So what is the value of a policy? It will basically give me, the value of a policy will basically give me VK, let's say there are just 3 states, and I'm looking for 3, if I'm looking for 3 horizon policy, then I'll say V3S1, V3S2, V3S3, then V2S1, V2S2, V2S3, V1S1, V1S2, V1S3, V0S1, V0S2, V0S3. That's the value function. I would say this is called a value vector. This value vector in this particular case is 12 steps long. It's a vector of length 12. Right? So in the finite horizon case,